You got another number for us?
I have, yeah. It's the, well, I'll just write it down, shall I? That's probably the best thing to do. So it is 10 to the 10 to the 10 to the 10 to the 10, and then this is the strange bit, to the 1.1. Okay? This has been claimed to be the largest finite time that has ever been calculated by a physicist in a published paper. This is the paper. It's a bit of a weird paper. It's not had a huge impact, I don't think. It's about black hole information loss and conscious beings. We won't go down that route. He actually calculates something called the Poincare recurrence time for a certain type of universe within a certain cosmological model, and this is the number that he gets out. So this is the one I'm on about. Let me just check I got the number of 10s right. Yeah, I did. Okay. Here, it's equation 16. So he's put Planck times millennia or whatever, because basically it doesn't really make any difference whether you use seconds, Planck times, millennia, years, when the number is this big. But there's other interesting numbers in here, which is this one here. You know, you've got 3 10s to the 2.08. That's the Poincare recurrence time for our universe.
What's all this about, dude?
Okay, so Poincare recurrence time. This is something that's arisen from statistical mechanics. Very simply, you know, if we had a pack of cards, and we've only got a finite number of cards in that pack, and let's say we keep dealing each other, you know, hands of 5 cards. Eventually, if we do it for long enough, you know, you're going to get a royal flush, Brady. That's guaranteed to happen. And then if you wait long enough again, you'll get another one, and so on, and so on. And that's true because there's a finite number of cards. Now, what Poincare realised is if you take a gas of particles, you can put a gas in a box. Now, you can put all the particles in one corner of the box, and then they'll disperse, and then they'll move around. But what Poincare recurrence tells us that after a very, 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 very long time, those particles will eventually return to the corner of the box. You always get a repetition. And it's basically because the thing that controls the evolution of that system only has a finite region of what we call phase space, of sort of solution space, that's accessible to it. And so eventually you always come back to an arbitrary close to where you started. The timescales are truly enormous before you start expecting it to happen. So you can apply this quantum mechanically as well. So when you're doing it in quantum mechanics, what you're really talking about is sort of the evolution of microstates within the quantum system. So, you know, the sort of quantum building blocks of your system. And they will eventually return, they will evolve, but eventually return to their initial state. And what Don Page in this paper has tried to do is he's actually applied that to various types of universe, models of various types of universe. It's a bit of a cheat because a universe is what we call a macroscopic object. It's a large object. It's not really a quantum microstate in some sense. What it is it's an ensemble, an average of all the microstates. So what he's tried to do is he's tried to say, okay, I'm going to treat the universe as this average of all these states, but then I'm going to count up all the possible averages and treat them as a sort of microstate in itself. So it's a bit of a cheat, but he gets an extra exponential out from that.
Are we talking about Jupiter's over there, the Andromeda galaxy's over there, I'm in this room filming you?
Yeah. All that, okay? Now, there's a very large number of possibilities that you can have, but it's finite. And so, as the system evolves, the system can only evolve through a finite number of possibilities, and eventually it evolves back to where it started. So actually, I've often heard it said that the universe, for example, will evolve, will expand. Eventually, everything will be very far, spread out very far because of the expansion of the universe. That all objects will have collapsed to form black holes. That then those black holes will have evaporated from Hawking radiation, and all you will have is this very sort of bleak landscape of just radiation and that's come out of these evaporated black holes that's uniformly distributed, and it'll be very boring, okay? But that isn't the end state of the universe. The end state of the universe is that after these truly epic timescales, you will eventually have a Poincare recurrence and you'll wind up back where you started from. And it's quite easy to see how it might happen. Imagine you have this sort of bleak universe, right? Just have a little fluctuation. That little fluctuation sort of, gathers together, builds up other things. Eventually it sort of forms a sort of galaxy even. From that galaxy you get planets, stars, and you keep going. Eventually you'll get back to a situation where it looks like it is today. Now, what I think is fair, I think is a fair point, is that there's no way of ever being aware of these repetitions over these large times. And the reason is you could never build a device, you could never be an observer that could measure this. And that's because over these huge timescales, such a device or such an observer would definitely thermalize, would definitely become part of this recurrence itself. And so there's never anybody or anything that could measure it. There's this sort of idea, you know, this sort of notion within physics is that if you can't measure it, it's irrelevant in some sense. So,
but according to this, in this number of years, you and I are going to make this video again. You and I are going to make this video again.
Ah, no, it's less than that. This is for a special type of universe that's particularly large. Okay, the number for us is at least less than this other number that he's written down here, which is 10 to the 10 to the 10 to the 10 to the 2.08. As I said, I'll just say years. Okay, so this one is the one that applies to us in this in our visible universe, what we call our causal patch. This one applies to seeing what is the Poincare recurrence time for a truly vast domain of universe that you can get out of certain models of cosmology. So they're all based, of course, on the same idea, and we can work through where these numbers come from. So the Poincare recurrence time of any system is roughly proportional to the number of sort of states in that system. Because we're applying this to the universe, this is really the number of macro states, the number of these averages of micro states that you can talk about. So let's call this n macro. This then, we'd expect it to be about the exponential of the number of microstates. Now, why is that? Well, this doesn't really have to be an e, this could be a 2 or whatever. Basically, any microstate is either in or out of the averaging with some weighting, and so this is the number that you get out. The number of microstates, when you relate to the entropy, is e to the entropy. Let's look at some volume of the universe, okay, of some radius r. Then the entropy, we've done this before, and it's the same argument as we had before. The entropy that you could possibly have in this region of space, basically it's proportional to, I'll just be a bit sloppy with factors, r squared over the Planck length squared. So the next step is e to the, so now let's apply it. So let's apply it to the really big number that he does, okay? So the question is, what's r? Well, the radius of the universe is about 10 to the 26 meters. Yeah, our visible universe. Okay, so as far as we can see, what we call our causal patch. The Planck length is about 10 to the minus 34 meters. So r over L Planck squared is about 10 to the 120, which is a number you often see in physics, actually. This is sort of the number that's associated with the cosmological constant problem. But anyway, well, 120 is about 10 to the 2.08. That's where that is coming from. I don't know why he's so precise about this 2.08. Because what he's going to do next is, so the number we have is e to the 10 to the 10 to the 2.08. But what he does here is he just approximates these e's as tens, which is fine, really, in the broader scheme of things. E, 10. For the sake of cosmology, they're more or less the same thing. All the e's become tens, and you get 10 to the 10 to the 10 to the 2.08. Which hopefully is what he's got there, and it is, okay? So that's where that number comes from. So this is basically the Poincare recurrence time for our visible universe, our patch.
Why is the other number bigger?
Well, because the other number is there he's looking at, he's trying to get a big number is why he gets it, he's trying to get a bigger number. What he's looking at there is a model of inflation. Now, inflation is a model of the very early universe, where the universe grew really quickly out of a very small patch of universe. The amount by which it blows up depends on various parameters in the model, but basically the thing that you get is you get that the size of the universe, so r, for that case, is of order e to the 4 pi over m squared. Okay, so this is actually r over L Planck. It really, he's done everything in Planck units. So that's 4 pi. M here is the mass of this what we call the inflaton field. It's just some field in the model that causes the expansion. 1 over m squared is 10 to the 12. I think this might be 13 actually. 10 to the 12. So this is about 10 to the 13, right, overall, because 13 is about 10. Okay, bear with me. So this is e to the 10 to the 13, roughly. The 13, well, is about 10 to the 1.1. That's where the 1.1 comes from. He's very precise about this 1.1, and yeah, he's very sloppy with some of the other factors. You get e to the e to another e to the 10 to the 10 to the 1.1, and then we do the same thing. We turn all the e's into 10s.
Help me understand, because I'm just how big numbers are. How long a time is this?
Okay, so this is truly vast. Like I said, there's no device, there's no observer, anything that could survive this kind of length of time scale. In fact, you would probably say that the universe is more likely to tunnel out of the current state before this could happen in some sense. This is such a long time scale that one might say that actually the probability of tunneling to a new phase of the universe, completely different, is actually going to dominate over this. That would occur first. So maybe this is a kind of a irrelevant point, but yeah, I mean, it's truly vast. I mean, it's bigger than a Google, clearly, way bigger. Is it bigger than a Googleplex? I think so. So, let's just check that. So, yeah, clearly it is. It's enormous. It won't be as big as Graham's number, but, Graham's number's the daddy, right? So, well, I didn't actually know about this paper, but I just thought, oh, big numbers. Let's see what's interesting about big numbers. And then I stumbled across this paper. It's well, he claims, in fact, he says it. He claims it's so far as I know, these are the longest finite times that have been explicitly calculated by any physicist. So whether somebody has calculated a longer one, and I'm sure some of the viewers will try to calculate a longer one and then claim that they've... but this is in a published paper, right? So you've got to get the paper published. But the challenge is on, I guess, to find a long one. There probably has been since, but he was the one that pointed it out.